AP Calculus AB, Unit 6, Day 4, Office Hours. This is the assignment that we did out of the book, page 267, 1 to 35 odd. All the odds in the back of the book, so you should check those already. I'm going to go ahead and go through these. Like I said, this might have seemed like an icebreaker maybe from the other rates problems that we've been doing. Y equals natural log of 2x. So when you take the derivative, dy dx or y prime, it's 1 over what's inside, right? 1 over what's inside times, often got to do chain rule, times the derivative of what's inside. So then the final answer is dy dx equals 1 over x for this problem. There we go. Number 3, y equals natural log of x all squared. Now, some of you guys might think, oh, I could bring the 2 out in front. Nope, that's only if the exponent is inside what's inside the natural log. So we can't do any log rules with this. So we're just going to have to do chain rule. Chain rule, we're going to do the outer rule first, which is an exponent. Leave the inside the same, right? Decrease it by 1, and then multiply by the derivative of what's inside afterwards. So dy dx equals 2 natural log of x over x. 5, y equals natural log the absolute value of tangent x. So dy dx is going to be 1 over what's inside times the derivative of what's inside. Derivative of tangent is secant squared x. Now, this absolute value stuff is probably throwing you off because tangents can be, positive and negative. And I guess later on, I'll show you why these absolute values actually end up going away. So secant squared x over tangent x. Now, we could maybe try and simplify this. Secant is 1 over cosine squared x, and then tangent is sine over cosine. So, we could flip it because we're dividing by a fraction. So I guess we could write this as 1 over sine x cosine x. I mean, you could try and clean it up. But just trying to see if I could. Yeah. I'll talk about the absolute value thing in the future at another time. We will bring it up. Well, okay, here's the deal. Absolute value, whatever is inside natural log has to be positive anyways, right? So then that'll force it to be positive. So that means it'll work wherever tangent is. Yeah, anyways, I'm not going to get further into that right now. Okay, 7, y equals natural log of x over 1 plus x squared. I guess with the absolute values, this is only going to work when tangent's positive. Now it'll work where it's negative. Okay. Now, let's see. So the derivative of this, dy dx, equals 1 over what's inside. So all of this is in the denominator. And then you got to multiply by the derivative of what's inside. So that's going to be quotient rule. So it's going to be low d high minus high d low all over low squared. This one's messy. So what do we get? We get, we could flip this 1 plus x squared over x, and then this is going to be 1 plus x squared minus 2x squared all over 1 plus x squared squared. So 1 plus x squared cancels with one of those. And then on the top, I'm going to rewrite it maybe, just combine like terms. So it's going to be 1 minus x squared over 1 plus x squared with another x. So that's fine. You're not going to be able to reduce this anymore. Do not cross these x squareds out. Please do not. You can try and factor the top, but you're not going to be able to factor bottom because it's not a difference of squares. So this is it. We could write it like this if you want, but there is no making that any simpler. Okay. Let's see, number 9 is y equals natural log of the absolute value of x cubed minus 7x squared minus 3. So again, I'm going to avoid talking about this absolute value stuff right now. It's going to be 1 over what's inside. And then times the derivative of what's inside, 3x squared. Now you really should put parentheses around this, minus 14x, because it's a bunch of terms. And so your final answer is dy dx equals 3x squared minus 14x over x cubed minus 7x squared minus 3. Okay, 11, y equals the square root of the natural log of x, which I would rewrite as natural log of x to the 1/2 power, because square roots are rational exponents, and they're just power rules. So we got to take the derivative of what's outside first. You cannot move that in front. It's not on what's inside the log, it's on the whole thing. So 1/2, leave the inside the same, decrease it by 1, and then multiply by the derivative of what's inside, 1 over x. Then we're going to clean it up, rewrite it without negative exponents, and maybe make it. This is going to end up in the bottom. Everything's in the bottom. So you have 1 over 2x square root of natural log of x. It's probably the nicest answer. 13, y equals cosine of natural log of x. So dy dx, chain rule says derivative of cosine first is negative sine. Leave the inside the same, and then times the derivative of what's inside. Natural log of x is 1 over x. Then we could write our answer a little nicer. Negative sine of natural log of x all over x. Okay. 15, y equals x cubed log base 2 of 3 minus 2x. So this one is not a natural log, so we're going to need that extra natural log of the base in it. This is definitely a product rule, right? And then you definitely got a chain rule in here. So it's good to see this stuff has time. We got to do the product rule first. So dy dx equals x cubed times derivative of this. It's going to be 1 over what's inside. But then you need the natural log of the base, because the base is 2. Then chain rule says you got to do derivative of what's inside, which is going to be negative 2. Plus log base 2 of 3 minus 2x times derivative of x cubed is 3x squared. Now, make sure you do not distribute this into this. We're going to put it back out in front. So our final answer, if we clean it up a little bit, is going to be negative 2x cubed over 3 minus 2x natural log of 2. You can leave that undistributed. Plus 3x squared log base 2 of 3 minus 2x. So you definitely want to put that. Now, you could switch the order here. This could be first and this could be second. Which might be the way the book has it, but it could be either way. Number 17. Y equals x squared over 1 plus log x. So we're going to have to do quotient rule on this one. Dy dx equals low d high minus high d low. Now log, that's base 10, so it's 1 over x, but then you need a natural log of 10. Low d high minus high d low all over low squared. So can we clean this up a little bit? We could, let's see. I mean, we could pretty much, you could just leave it like this, I guess. Something kind of, well, I mean, we could make it a little nicer. You got some options. Here, we can reduce that. I mean, you usually don't like fractions and fractions. So, I mean, I would probably suggest multiplying everything by a natural log of 10, top and bottom. So at least you don't have complex fractions. So this would be 2x natural log of 10, 1 plus log x. You could distribute that if you want, minus x, all over natural log of 10. I would probably leave the denominator factored. So, I mean, I kind of like this. I think the back of the book has something like this. So I usually don't want fractions and fractions for final answers, though. Okay, 19. Y equals e to the 7x. So we've done a lot of natural logs. So here's some exponentials. So dy dx equals, it equals itself. Do not do a power rule. Do not decrease it by 1. But you do need to do the chain rule, derive what's inside. So dy dx equals 7e to the 7x. Your best final answer. 21, y equals x cubed e to the x. You definitely need a product rule here, okay? So we're going to do x cubed times derivative e to the x is just e to the x, plus e to the x times derivative x cubed is 3x squared. Final answer, dy dx equals x cubed e to the x plus 3x squared e to the x. Probably be the way I would do it. I mean, if you want, you could factor it, which usually we don't want to start unsimplifying, but I think the book has this. They factor out the GCF, x squared e to the x can be divided out of both of these. There's x left here and a 3 left here. This is what the book has. I don't think that's any better. If anything, it's worse than the other one. 23 is kind of a weird problem, and there's a couple different ways you could go about it. So I'll show you a couple different approaches. It might be good to just watch both, just to kind of have an idea of things, option ways to attack problems. And sometimes one is better than the other, and sometimes another one is. So we could just attack it straight on the way it is, which is the least creative, but maybe not the nicest. So we could do quotient rule. We could do low d high. Now d high is going to be e to the x minus the derivative of e to the negative x is e to the negative x, and then you can multiply times an extra negative 1 because the chain rule. Low d high minus high d low. Derivative low is going to be e to the x plus e to the negative x times derivative what's inside, negative 1 chain rule. So low d high minus high d low all over, don't forget, low squared. Now, this is really ugly. I don't want negative exponents. I don't want fractions and fractions. So, I mean, we got a lot of algebra to clean up here. So, I mean, we could do all this. This is going to become a positive, right? This is just going to be a minus. I'll move that there. And then we got to FOIL these. So it's going to be e to the x times e to the x is e to the 2x plus e to the 0, e to the x times e to the negative x. You add their exponents. Plus e to the 0, which is not 0, it's 1, plus e to the negative 2x. So that's the whole first one, plus e to the 2x. Both of these are low d high minus, I got to be careful, I almost messed that up. Low d high minus high d low. Now here, it's a positive times positive, then it's positive times negative, so it's going to be negative e to the 0, negative e to the 0, plus e to the negative 2x. The bottom, we could multiply that out also. It's going to be e to the 2x plus e to the 0 plus e to the 0 plus e to the negative 2x. This is going to clean up nicely. That's a 1, 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 that's a 1. And then we got to distribute this negative. So what happens here when we distribute this is we have an e to the 2x and then minus e to the 2x. They cancel each other out. And then we have a 1 plus, we have a 1 plus 1, another plus 1, another plus 1, because we get negative times negative. The e to the 2x is canceled out. So on the top, we just have 4. I mean, so this is what we have now. If we want to write it without negative exponents, we could think of this as 1 over e to the 2x and multiply it by e to the 2x. So, I mean, I'm thinking this is okay. We could change it. We could write it 4e to the 2x over e to the 4x plus 2e to the 2x plus 1. That's another option. You could just leave the bottom in its original form squared, e to the x plus e to the negative x squared. That'd be okay. So that's one way of doing the problem. Now the book, I think they might have, their answer might be this one, 4 over e to the x plus e to the negative x squared. So they left the bottom undistributed. But let me give you one other quick approach to this, okay? What if instead, at the very beginning of the problem, we rewrote it without all the negative exponents and we cleaned it up right away? So it'd be e to the x minus 1 over e to the x over e to the x plus 1 over e to the x. It's not very hard. It's actually pretty easy. Multiply top and bottom by e to the x and distribute it. You get e to the 2x minus 1 over e to the 2x plus 1. Now, sorry, you can't see that. So I'm just changing the original problem, cleaning it up first, and then do the derivative, which I think is going to be a lot cleaner. Because, I mean, there's way less e to the x's. There's no negative exponents anymore. I just think it's going to be easier for a lot of reasons. Low d high minus high d low. Derivative e to the 2x is e to the 2x times 2. Derivative plus 1 is 0. All over low squared. Now you still have some, you don't have to do all the FOILing stuff, right? So it's going to be 2e to the 4x plus 2e to the 2x minus 2e to the 4x plus 2e to the 2x. And the bottom we could probably just leave like this. Now, by the way, yeah, I'll show you. I'll connect this to the other one. So these terms cancel out, and we get 4e to the 2x over e to the 2x plus 1 squared. That seemed way easier. Now, that's the same as this answer up here. Because if you were to factor this, this would be e to the 2x plus 1 squared. Right? So we got that nice answer without negative exponents, without fractions and fractions pretty quickly, a lot easier. So I don't know, just things to consider. And then if you wanted to, I mean, you could multiply the bottom out. So I kind of like that. Sometimes you should consider maybe making some changes to the original problem before you dive into the derivatives. Okay, 25 is y equals e to the x tan x. Ooh, this looks interesting. So you definitely have a chain rule. So the first thing is dy dx, derivative e to anything is itself. And then chain rule says you got to multiply by the derivative of what's inside. But then in here, it's going to be a product. So you better put parentheses. It's going to be x times derivative tangent is secant squared plus tangent x times derivative x is 1. And so that's it. I mean, we could sort of clean it up a little bit. I mean, I think this is fine. You could distribute it if you want, but so it's kind of scary looking one, but turned out kind of quick. 27 is y equals e to the parentheses x plus e to the 3x. Okay, so first of all, everything's inside of an exponential, so it is its own derivative. So that stays the same, right? But then you got to multiply by the derivative of what's inside, which you better put parentheses because there's multiple terms. Derivative of x is 1 plus derivative e to the 3x is e to the 3x, but then it has its own little chain rule, the derivative of what's inside. You got to use these parentheses. So the answer, I mean, it's kind of ugly, but I mean, it'd be fine to leave it like this. You'd want to put the 3 in front, and then usually put everything else in front of the other. You could distribute this if you want, but I think that's fine. 29, y equals natural log of 1 minus x e to the negative x. So dy dx is going to be 1 over what's inside, no matter what's inside. And then you got multiply the derivative of what's inside. Now the derivative of what's inside, that's going to be 0, but there's a product rule here, right? So it's going to be negative x times derivative of e to the negative x is e to the negative x times derivative of what's inside is another negative 1 plus e to the negative x times derivative of negative x is negative 1. So that's it. That's the derivative. Now we just got to try and clean it up. So, I mean, this is, the top is going to have what? It's going to be positive x e to the negative x minus e to the negative x over 1 minus x e to the negative x. So, I mean, I guess you could leave it like that, but it has all those negatives in it. So we could try and clean it up and rewrite it as x over e to the x minus 1 over e to the x. So one way is to get rid of the negative exponents by moving them to the denominators. And then you have fractions and fractions, but that's an easy fix. Multiply top and bottom by the least common denominator. And you get x minus 1 over e to the x minus x. Wow, that's nice. I cleaned up nice without too much crazy effort. All right. All about the details. Okay, we got a few more. Okay, these ones say 31 says find dy dx by implicit differentiation, which I guess you kind of should just recognize that you should use implicit differentiation because you don't have y solved by itself, and solving for y by itself I don't think it's going to happen at all, and it would just be a ton of extra work, and the derivative would probably be worse in that case. So we're going to take the derivative with respect to x, so dy dx plus 1 over what's inside times the derivative of what's inside, which is a product rule. X times the derivative of y be dy dx plus y times derivative of x with respect to x is 1 equals 0. So that's it. We did the derivative, but now we got to get dy dx by itself because that's what we're trying to find. So I would probably go ahead and distribute this. It's going to be 1 over y dy dx plus 1 over x. And then we could factor the dy dx out of the two terms that have dy dx 1 plus 1 over y and move our other term to the other side. And then, then you're going to divide both sides by this, right? But you might change this to like a single fraction so that you can, change it to multiplication. So you can't just flip this the way it is. So least common denominator would be the same thing as y plus 1 over y. So I'm going to multiply by that reciprocal instead of dividing by. So it's going to be negative y over x parentheses y plus 1. So you can do that. You do negative y over xy plus x. That's fine. Um, 33 says, use the method of example 3 to help perform the indicated differentiation. So you should probably go back and look at, well, what's example 3 in your textbook? And it's just like a couple pages before. And what they suggest in that example is that if you're taking the derivative of a log, use log rules to break it up first, because this derivative is going to be horrible. But if you use log rules, you can break it up first. You can say, oh, okay, well, this would mean natural log of the top minus natural log of the bottom. So that just got rid of a quotient rule, which I think you would like. We could also change this to a 1/2 and move it out in front. That gets rid of an extra chain rule step. So I haven't done any work here. I've just like just rewritten it. Now, I think that's about as far as we can go with this one. But if you use log rules to break it up, it makes derivative a lot easier. So now it's going to be 1 over cosine x times derivative of what's inside is negative sine x minus 1/2 times 1 over what's inside times derivative of what's inside. And you're done with the derivative. Leaving it the way it originally was and doing derivative that way would be horrible. This is negative tangent x plus 3x over 4 minus 3x squared. So if you take the derivative of log or natural log, use log rules to break them up first. And it breaks the derivatives up and it avoids some really complicated, you didn't have to do quotient rule anymore, you didn't have to do the chain rule as much. It just makes it a lot easier to break down. So 35 is kind of similar. It says using the method of logarithmic differentiation. So essentially, do what we just did. But the problem here is that there isn't a log or natural log to begin with. So this is kind of an extra level technique where we say, oh, you know what, this is going to be a crazy derivative. But if we bring natural logs into it, we can break it up and make it easier. So I'm going to take the natural log of both sides, which I'm allowed to do. And I think this is a cube root, so I'm going to make sure I don't think the cube is on the x squared. So take natural log of both sides, bring the natural log in, and then use log rules to break this up. This is going to be natural log of x plus natural log of cube root of 1 plus x squared. Right? And then we could even say, oh, this is a 1/3 power. Let's bring it out in front. So now the only thing is now you have to do a little implicit. On the left-hand side, you got to do 1 over y dy dx. So this is a problem that we're going to do implicitly that wasn't really, it was ready for explicit, but we complicated it to make things easier. 1 over x, right, plus 1 over, or 1/3 times 1 over what's inside times derivative of what's inside, chain rule, and then that's it. Now, we want to get, we want this right here, dy dx. So we're going to solve for this. So it's going to be dy dx equals 1 over x plus 2x over 3 plus 3x squared. But then we got to multiply by y. Right, both sides by y. I don't want a y in my final answer. If it was designed to be implicit to begin with, then fine, we can have y's in the answer. But since we made it this way, it's easy. This is what y is, so we can just plug that in right there. and now it's all in terms of x. It's a pretty ugly answer, but it's better than the alternative. I mean, you can do it the way it was originally written, but be pretty messy. It might look a little different. It should be the same, but it's just an idea, something to try, to use things about logs to help make derivatives easier. Even if logs aren't in the problem, you can use it. You can introduce it. So that's called logarithmic differentiation. All right, that's it.